also a new like tester module for Pytherium, which Vitalik wrote, which I will also integrate because that simplifies a lot of the logic that I was using. And the other front is just porting the tester module. Porting Vitalik simple Casper tests to the new tester module. And the reason why there's a new tester module is because now it supports chains. Because the other tester was just like modifying state and like state transitions. But now this has a concept of blocks and chains, which is great for, implementing the fork choice rule.
Oh, cool.
That's essentially it.
Cool. That sounds great. Virgil, did you want to go next? Okay. Okay. All right. Well, I'm almost there. 1 second.
Take your time.
Yeah. Yeah, it's one of those. I got a little distracted this week because I was looking a little bit more carefully at integrating the ideal adversary calculation with this double perp close stuff, and so that's why I don't have the diagrams quite ready. I was looking in particular. Carl, did Vlad ever mention Moran processes?
I recognize the name, so I feel like you may have tossed it out there, but I don't know exactly.
Okay, all right, yeah, because I think that the ideal adversary calculation closely resembles form a Moran process. Yeah, so, and there's a couple of papers that I found that give lower bounds, interesting lower and upper bounds. So I was kind of taking a look at those, and I can paste the links to all that stuff in the chat. And I just wanted to quickly, I'm almost done with the diagram here. And then I can, yeah, because I want to show at least the traced composition. Let's see, there we go. I feel like I've given this diagram before, but just in case. There we go. And then I think these two go in. Yeah, that's right. This. Okay, good. I think that's it. All right. And then there we go. So then we can kind of label this. Good. Okay, there we go. So I'll now do a screen share and kind of Okay. So, what I'm describing is in this diagram is a composition, and I'll try to make it clear by labeling it. But before that, I need some definitions. So let's say I have a row-line contract, P, and a row-line contract Q. Then we say that the two annihilate each other, which we write this way. Can people see that?
Yep.
Okay, cool. If for any contract state R, if you run P in parallel with Q, so they can potentially talk to each other, whenever they evaluate to eventually get to a contract state R, then that implies that R eventually terminates, gets to 0. So that means that these two as effectively exhaust each other's interaction with the world. And the most simple example is that if one is sending and one is receiving, or actually the simplest example is P is the stopped contract and Q is the stopped contract. And if you run those in parallel, then that reaches the stop contract state, which is the same as the stop contract state. So 0 annihilates 0. And that's the base step of all the inductions that we do. From there, you know that if P is sending on the name of the contract 0, and Q is receiving on the name of the contract 0, and then both of those stop after that, then those two annihilate each other, because after one step they go to 0, and 0 is 0. So so this shows that not only is this well founded as a recursive definition, but that there's an infinite set of annihilating contracts. There are contracts that annihilate each other. So there's plenty of these this kind of relationship to go around. And now we say, given a set of names sigma, so names are in this setup the codes of contracts. Then we define sigma perp as the set of names Q. So these are the names of some contracts Q, such that you can find a name in sigma such that P annihilates Q. So again, just to be clear, Q is going to be some contract. At Q is effectively the name of that contract. So these are names of contracts that annihilate some contract, the name of which is in sigma. So that's what sigma perp is. And then we say a set of names, sigma is double perp closed, if and only if sigma is equal to the perp of sigma perp. So when you can calculate this set of names, and then from that set of names, you can perp it again and calculate a new set of names. And if you get back to sigma, that's double perp closed. Sigma is double perp closed.
In the chat, Virgil asked what the period after for all R period.
Oh, that's math notation for such that.
Cool.
Yeah, it's the scoping operator for the quantifiers. Okay, so all right. So then we're going to let T, U, V, W, etc. range over triples of the form sigma, phi, and tau, where phi is a formula from the namespace logic or the type system of Rolang, and sigma and tau are triples, are double perp closed. And what you want is you want that sigma is a subset of the meaning of phi. So you can think of phi as an extra filter. So it insists, so you get to pick double perp closed subsets that are somehow complements of each other with respect to phi. So that's the notion of type here. And then we're going to build a notion of we're gonna build a notion of a second level process calculus. So the idea is that double perp closed sets of names are going to be the things from which we can receive and send. So the notion of channel is really sets of processes. And this shouldn't be terrifically strange. And the reason it shouldn't be terrifically strange is because we're used to sending something over TCP/IP, and yet TCP/IP is really built out of a bunch of little processes that are ensuring the sliding window protocol. And then above that, we're used to sending things over HTTP, and HTTP is really made up of lots of little processes that are ensuring the semantics of the HTTP protocol. So this idea of sending over something more complex than just a simple channel is actually quite familiar to us from actual engineered systems. So it shouldn't be strange at all. But here we're just making it a little bit more formal, a little bit more explicit. And so what we insist is that the sigma and tau have this perp relationship. So the things in here are screwed up by or evaporated by the things in here. I should also include that tau perp is equal to sigma. So that's a condition I should have added. So we need both conditions. And given these conditions, then if this process is waiting on sigma for some input and then becomes P, and that's running in parallel with the process that's sending on tau some double perp closed set of names, then we can go a step forward in the process or go a step forward in the contract, and we to a new contract state, which is effectively P, in which chi, this set of names, replaces x in y in P. So that's the basic shape of the sort of contract that we're considering. And now what we're going to do is, and I can just quickly provide a definition. I'll steal it from here. Just grab it here and modify it. So the first thing is, well, I'll cut to the chase so that we don't have to build up too much. Okay, so now we say that P runs from T to U. It's useful to add that extra layer because the type algebra is important. Okay, so we define T to U to be essentially sorry, this should be range over sets of triples. Okay, like that. That's a little better. Okay, and then TTU is now just T disjoint union U. So, and in particular, what this implies is that the free names or the names in these sets are disjoint from each other. So these things don't intersect with these things. So the sigmas don't intersect with the taus. I'm sorry, the sigmas in T don't intersect with the sigmas in U, and the taus in T don't intersect with the taus in U. They're disjointed. And in fact, we can go a little bit further, but for purposes of discussion, we don't need to do that. And then the only thing, so then we have one more step before we get to this, which is we say P satisfies T if and only if the free names of P, oops, whoa, oh, I see, it's doing that for me. I don't want it to do that. Is equal to the projection of the sigma projection of tau. So that's sigma. Oops. There, where this is just the first projection of these triples. So it pulls out sigma, so of each of the triples. So the free names is complete. The free names of P are completely described. So what do we mean by that? That means all the places. You can think of it as all the addresses that the row-line contract P interacts with. So these things are now can be thought of as addresses. So all the addresses here are described by T, by a sigma of T. So the first projection. So we pull out. We have T is a set of these things. We pull out all of them from T, and the free names or the set of addresses where P can gauge is exactly that. And then it is clear that since that's the case, when we have P satisfies T arrow U, then the free names of P is going to equal to sigma of plus of U. And sorry, I need to do one more thing here, which is to go grab this to be absolutely accurate. Okay. So we go through and we perp all the things in T. So this perps the things, the sigmas, and it perps the taus. Right. So that's what this construction here does. And so then this is going to be the sigma of T perp Oh, stop that. There we are. Okay. There's sigma of T perp plus sigma of U. So that's the construction. Now there is one other tiny little requirement, and that is that the processes that we build here are polarized. So what do I mean by that? And I can draw that diagram very easily and very quickly. And I'll just put that on the same page here. And then we can talk about what's happening here. Okay, so what I mean by polarized is that we have I don't know, if anyone has any questions, please don't hesitate. Okay, it looks like people are still there.
Yeah.
Okay.
Sorry about that.
yeah, no worries. Okay, so let me just go grab the fonts. Okay, and then grab Optima. Okay, so the idea is that you have T here, and it's kind of in the, and then this is U, but the important thing is that they're in opposite polarities. Now, what do I mean by polarities? So this has to do with the perping. It's, you know, this is sort of perped with respect to this. So they're, and then on the other side, they're flipped around. Okay, so and I've made a nicer diagram here. Yeah. But okay, so you can think of this as in the negative polarity with respect to the previous, with respect to the other one. Maybe it would be easier for purposes of discussion if I just flip it around. That'll be easier. It doesn't matter. It's completely symmetric, but it might be easier for discussions to do it that way. Okay. So this one is in the positive polarity, and this one is in the negative polarity. And then on the flip side of this, it's like this. This is in the negative polarity, and this is in the positive polarity. Oops, that's weird. Okay, and then over here, so think about it like this. P can only read on the negative polarity forms of the names and write on the positive polarity forms of the names. Read on the negative polarity forms of the names and write on the positive. Okay, so if P and Q are going to communicate, then they have to have both sets of polarities, right? So here they would communicate like this. So it would that's weird. So it would read on the, so this would write, and let me flip these around, it'll be easier. So we have like that. So P would write on U, and Q would read on U, and Q would write on T, and P would read on T. So that's a subtle, that's a kind of a subtlety to how the processes are wired up. But this is really just the twisted pair construction, right? So all we're doing is saying, let's put it this way. Go ahead and put these in. And then over here, these polarities are reversed. So that's plus, and that's minus. But now let's get these lined up in a slightly better way. Okay, so I'm worried that I will run out of time here. So let me skip to one that I had prepared in LaTeX. So hopefully that won't be too hard. So here I was just trying to make the notation as consistent as possible. Here in the LaTeX form of this F is P and G is Q. So let's see if I can just write over that, if that'll work. It may or may not work. Yeah, it'll probably not work. Okay, so essentially, you've got the positive part on the left-hand side for the first component, and the negative part on the right-hand side, and the negative part on the left-hand side, and the positive part on the right-hand side. And now, when we compose, what we're going to do is we throw in something called the trace, which is going to eliminate this bit, and I'm going to show you how that's done when we compose, right? So that's in relationship. So there's a base level of erasing, and then there's a kind of iterated erasing. So the base level of erasing is when we compose just at this level, we're going to use the taus to multiply by to multiply the sigmas by. So let's define that really quickly. I'll need one more page here. Okay. Okay, and then I'll do, so we want this one here. Okay. So you have P, and P runs from T U, and you have Q, and Q runs from U to V. All right, so that's the setup, and we want to glue them. So we're going to define a new operation, P, and we'll do dot Q, and this is going to be P in parallel with Q. So we're letting them interact, but we're going to do something tricky, which is, remember, the things over here are in opposite polarity from the things over here. So they can be glued, and we know that they annihilate each other because they're in exact duality by the requirements, right? So the sigmas and the taus are double perp closed. So over here you have the perp of sigma, over here you have sigma. So they exactly annihilate each other. And over here you have the taus, and over here you have the perp of the taus, and they exactly annihilate each other. So what we're going to do is, and remember that P and Q are only interacting on the sigmas. They don't interact on the taus. The taus are outside of our safety specs or our liveness specs. They're sort of a special namespace. And that special namespace looks like this. You take all of the sigmas, so every every name in sigma, I'm using P's and Q's, so I need another process name. I'll use R's. Okay, so we have at R. Okay, so all the at R's, and you're gonna replace them with an at R times an at S from the tau. And that, so this is scoped. These are the at R's that live inside sigma. Of U. Okay, so now I need to tell you what times means, and that's pretty straightforward. It's just oh, I see it does. That's weird. I don't know why it does that. So we have at R times at S is just equal to taking the at of R in parallel with S. So this is the name of some contract R, and this is the name of some contract S. So you can think of these as taking references to them. So we have some special laws on taking references of contracts and getting back from contracts to references. Are there chats? That's correct. There's they almost refer to sets. So what it means is this is standard from these kinds of calculi. So when you write P y for x, what you're saying is substitute y for x in P. This represents a substitution. So you could think of this as a partial map from names to names, and which can be uniquely lifted to a partial map or to a total map from processes to processes. So you wander through here. You look at all the free names, the ones that aren't bound by an input operation, a for comprehension. Whenever you find an X, where the X is, you replace it with a Y. Now, and then we lift this up to operating on sets. So we're not just going to do this with a single substitution. We're going to build up partial maps in this style where the source of the map is that all the at R's in sigma tau, and the target of the partial map is this new name here, right? So this is the replacement operation, and then we apply it all the way through. Let's see, hopefully. Coolio. Awesome. Okay, so that's sorry. That's I just assume that is background knowledge, but I understand if you don't have the process calculate or lambda calculate, then that would be unfamiliar notation. Okay, so I've now given. This is effectively realizing parallel composition plus hiding. All right, so what we do is we get a new process, and the free names of this process are going to be the free names of this process are going to be just the T perp and the V perp, right? So P and Q are again, they're polarized. They only write on twisted pairs, right? So that's this picture here. Right? So they only write to each other on twisted pairs. And then the next step of the puzzle is when we compose them by hiding the place where we glue. So we're going to glue along here. Let me grab one of these. So we glue along here. And then we hide this portion of the we hide this portion of the place where they're glued by multiplying by these taus that are sitting in the triples. So this is our. It's a way of you can think of it as a technical convenience, but what it's really doing is saying that you could think of these as performing the property of shifting the namespace into shifting all the places where they're interacting into a private namespace. So these are the names or the channels or the addresses, however you want to think of them, where the interaction is happening. And you could think of these as either the cryptographic primitives that are hiding the content, or you could think of them behaviorally as forwarders or private channels, or however you want to think of them. This multiplication operation. You could think of it also as a Diffie-Hellman kind of construction. But this multiplication operation is saying that no adversary can get in on this bit and screw up the communications along the U common bit, which is here. So I should really rename these slightly. So let me be slightly more a little bit more consistent. So what we really want to do is to think of each we're going to add a layer of complexity that has to do with the trace, and I'm probably going to have to get to that next time. But each process has really got, or each contract has really got an additional chunk in it, an additional chunk of names, which is going to be representative of common state between the two. And what the trace is doing is it's eliminating or erasing the common state and making sure that the two agree on the common state. So that's the blockchain operation. So what we've done so far is just to build up this idea of parallel composition plus hiding. So far we've just said what the processes are, and then we've said how how the channels interact with each other, so that they affect, so the communication over the channels we know terminates. That's effectively what this definition is, and the double perk close condition. So that's the requirement there. And then so you could think of these, as I mentioned last time, you could think of these as effectively the communications amongst the validators, right? So this thing here, these two pairs of conditions are requiring that this set of names, which is really a one level down set of processes, so those two processes are interacting, and you could think of those as effectively the validators. It's not exactly one-to-one, but it's not bad from an intuitive point of view to think about that. So each name is, as we said before, representing the interaction of representing a process, and then these processes, when they run together, annihilate each other. That's what these two conditions are. And so really what's happening is you're running the validation cycles to completion before you effect the communication. So these conditions plus this situation says we don't affect the condition or observe this state update. That's really what this substitution is. It's a state update. So at y, we now observe the value chi, right? That's really the meaning of this expression, and that happens when the interactions over sigma and tau come to termination. And then the next level up is we're saying not only do they terminate when we glue them together, but we're going to hide that communication from attack. So that's what this definition here is doing. We're insisting that the taus represent, so again, the taus which live in these triples here, and which are also double perk closed, and that ends up being a technical requirement, because if you do the multiplication here, you might not get the coming to quiescence. So the taus act as cryptographic security, and don't allow an attacker to come into and screw up the terminating process. So that's what's happening there, and why that's necessary. So then the picture that we're creating is we glue along these lines here, and then we multiply this gluing by the cryptographic machinery, and then this becomes this picture here, where all of this part is erased. Basically, I want to take this out to the middle and this out to the middle. And the external world can't see this part. Right? So the external world can only see a process that looks like this. It looks like a single contract that's running from here to here. And then we're almost out of time for Casper, and I should still have more of the diagram done. But essentially, what we're going to do next is we're going to trace out the common parts. So we're going to hide. We're going to do an additional sort of hiding by removing the common part with an iteration. So which amounts to Remember, we have this thing here, and that's the actual execution of the processes that are the names. So we're going to run the annihilation and let them, because we know that they terminate. So that's what this thing here is. So flipping around like this and coming in like this and flipping around like this and coming in like this. Think about it this way. Input can come in this way, and either it goes out or it's impinging a part of the contract which is on the common on the place where P and Q or F and G respectively have to agree. So if they have to agree, then you have to run the annihilation process to get it to terminate. So you'll run out here and come back around into G. So you went out F and you come back into G, right? And then you have two possibilities. Either you've completed the annihilation, so you have an agreement on the common part of the contract, or you come out, in which case you come out this way and show up on the outside, or you are still in the annihilation part, in which case you come out this way, you go around like this, and you come back in on F, right? So we came in, we entered F or P, we go out through B, come back in on G or Q. Sorry, the notation wasn't consistent between the slides. That's what I'm cleaning up. And then you come, if you're not done with the annihilation process, then again, you come out on B, you run around, and then you enter back into F, i.e. P, and then just make a decision. Have we come to an agreement? Do these two agree on the common part of the blockchain state? Or, which is, effectively, are they consenting? In which case, we come out on this line. Otherwise, we go back around the loop. And you can prove that this, we can prove a lot of things, but one of the most basic ones is you want to prove that this is associative. So we can prove that it's associative and a bunch of other stuff. But in particular, the next step is to show that when you have a construction like this, then you get agreement on the common part. That's consensus. And when you have a means of getting agreement on the common part, then you can always build a diagram like this. So that's what I'm in the process of writing up, and then we'll look at what it means when the trace is faulty, when it's not complete. In other words, there's some means by which it can be screwed up. Looks like there was some comment there.
Cool.
Yeah.
Yeah, I'm starting to understand this diagram that you.
Cool. Yeah. It takes a while. It takes a while to absorb it. There are a lot of moving parts, but. Yeah, I understand, Virgil. It's a different world. It's a different way of conceptualizing both information and computation. The essential, the core essential difference between information theory and the calculi point of view, in particular the point of view that's espoused by the lambda calculus and the pi calculus and the rho calculus, which is what I use, is that being is doing. So if you look carefully at the lambda calculus, there's no such thing as data. In the pure form of the lambda calculus, you arrive at things like arithmetic as the behavior of programs. So numbers are programs, and addition is a program that operates on programs, and so on and so forth. So there isn't such a thing as, or information is reified as behavior. And then the category theoretic point of view, kind of, which is what we're doing here. When we look at these diagrams, the category theoretic point of view mediates between those two viewpoints in a certain way, right? So it's saying that, I can treat certain behaviors as if they were data, and I can classify those. So that's what the A's and the B's are, is classifications. And then other forms of behavior look like computation as opposed to data. And that's what the F's and the G's are. So that can help with some orientation. And in client, getting the notation, it just, it takes a little bit of practice. All right, I'm done. I know it was a long-winded update. I apologize. I monopolized the time here, but looking forward to talking with everyone next week. Are there any other burning questions, comments, thoughts?
Not for me.
Sweet.
Cool.
Yeah, Virgil, that's what this is all about, is I'm getting, well, there's lots of papers on the background. I can send you links, and I'll put links somewhere. I'll put links in the Casper chat. I've done that before, but they disappear. Yeah.